Hi guys, Dr. B here. This is a lecture on gas properties and gas laws for 2026. So a few properties of gases, they fill the container that holds them. The shape of a gas is the shape of its container. So whenever you put the gas in, it will take that shape. Every bit of the volume is filled with gas from top to bottom. Gases can be compressed to smaller volumes or expanded to larger ones. So if you did the gas properties lab, you saw that you can decrease the size of the container, which will compress it, or you can increase the size of the container, which can increase the volume. Temperature, pressure, they can affect volume. That's the whole point of this particular lecture and the properties of gases. They like to, they tend to spontaneously mix with one another to form mixtures. So if you have, like in the classroom, you have nitrogen, you have oxygen, you have noble gases, you have water vapor, very humid type of thing, where you put the gases together, they're going to form together, and they're going to mix together, forming a homogeneous mixture. Gases exert a pressure that is constant and uniform in all directions. That's why when, like for example, you pump air to a tire, it's a the pressure exerted from the gas, that's what you feel like the firmness of the tire or whatever it is you're inflating. Gases can change their volume, and that's what we're going to be talking about here, the effects of pressure and temperature and the amount of gas on a volume. So pressure is measured with something called the barometer, and it was historically developed using mercury. And the height that it went, that was the pressure, if you will. So that's where the term millimeters of mercury comes from, mmHg. At sea level, the average atmospheric pressure is 760 millimeters of mercury, which is used as a standard for pressure. One atmosphere or one ATM equals 760 millimeters of mercury. So where we live at currently, uh, sea level, the pressure is one atmosphere, it is 760 millimeters of mercury. Pressure can be defined in different ways. I'm sorry, like the units can be different ones. So, for example, millimeters of mercury, that is mmHg. That is also called torr, named after Torricelli. So the same number, 760 torr, 760 millimeters of mercury. Atmospheres, or ATMs, ATM, Pascal, that's PA, and then kilopascal, kilopascal is 101.3 in terms of one atmosphere. So one atmosphere equals 760 millimeters of mercury equals 760 torr equals 1.013 times 10 to the 5 pascals, or 1.3 kilopascals. So since they all equal one another, you can use it as a conversion factor. So 485 millimeters of mercury, converting that to atmospheres. So let's see if I can put that. Let's see up here. 485 mmHg over 1 atmosphere, 760 millimeters of mercury. So it's going to be 485 divided by 760. So we have 0.638157. That's going to be my answer, but I got to think sig fig. So three significant figures. They should also be three significant figures. So my final answer will be 0.638 ATM. Don't forget your units in your box when you're answering. 556 torr, convert that over to kilopascals. So 760 torr on the bottom. Your conversion will be to kilopascal, so 101.3 kPa. So it looks like our denominator is 760. Our numerator will be 556 times 101.3, or 56322.8. Divide that by 760. So 74.108. So 3 sig figs. So the final answer should be 74.1 kPa. 2.50 ATM, convert that over to atmospheres. So 1 ATM equals 760 torr. I multiply across, I will get 1900. But because the number I gave you as 3 sig figs, to make this 3 sig figs, it would be 1.90 times 10 to the 3 torr. When working with problems with gases, make sure your temperature is always in Kelvin, not Celsius. So if you're given a temperature in Celsius, you'll add 273 to make it Kelvin. There's no degree symbol present for Kelvin temperatures. So make sure you're aware temperature in Kelvin is Celsius plus 273. There are 6 gas laws that we usually cover: Charles's law, Boyle's law, Avogadro's law, combined gas law, ideal gas law, and Dalton's law. For this, shortened Unit 9, 2026, we are, most of these, actually all of them you have to be able to recognize. For some, you're going to have to be able to solve problems. What I mean that is that you're going to have to list your knowns and unknowns, write out your equation, plug in your numbers, make sure your temperature is in Kelvin, answer to the correct amount of sig figs, and make sure you include your unit. When I say you need to be able to recognize, that means I'm going to give you the formula, and you'll have to know what is the law that's being described in the real life application, whatever the relationship is. So Charles's law, the volume of a gas varies directly with its Kelvin temperature as long as the pressure and amount of gas is constant. So varies directly. That means if I increase one, the other one increases as well. If one goes down, the other goes down. They both follow the same direction. So V1 over T1, initial volume over initial temperature, equals final volume over final temperature. Real life application, so you measure the pressure of your car's tires when they're cold. So when they're cold, you're measuring the pressure, technically measuring the volume as well. The driving heats up the tires, and eventually the air expands. When tires are warm, they will tend to be higher than normal. So you need to double check that your tires are overfilled or not overfilled, especially when they've cooled down, because eventually what happens is the pressure, well, the volume will decrease as well, and that can cause problems. Like if it's actually low because the volume is low because of the temperature, or is it because it's actually you've lost air type of thing, you have to make sure in case your tire doesn't explode or whatever the case may be. Boyle's law, so it's how pressure and volume are related. So pressure and volume vary indirectly. That means as one goes up, the other goes down. They are inversely related. So if I double the pressure, I half the volume. The formula, is P1 V1 equals P2 V2. Initial pressure times initial volume equals final pressure times final volume. One goes up, the other goes down. So in terms of real life application, scuba diving, as a diver descends, the water pressure around them increases, causing the air to occupy a smaller volume. Air compresses in the ears. You must equalize your pressure to avoid pain and possible injury, called ear barotrauma. As a diver ascends, water pressure decreases. So Boyle's law states that the air in his ear and body expand to occupy a greater volume. That's why you have to be careful when you are scuba diving, not free diving, but scuba diving. You have to make sure that you ascend slowly and a kind of a staggered pace, because if not, if you ascend too quickly, the nitrogen bubbles that are in the in the tank that are really circulating in the blood may expand, and where they expand, it can cause different symptoms, different problems. Okay. So don't really hold your breath underwater if you're diving, because if you ascend too quickly and there's air trapped in the lungs, it will expand, causing pulmonary barotrauma. That means lung trauma due to pressure changes. So another term for this is it's actually called decompression sickness. Decompression sickness is caused by diving and ascending too quickly with uh, nitrogen bubbles locked somewhere in the blood vessels. It can be in the lungs, it can be in the brain, it can be in the stomach, it can be in the joints. That's why decompression sickness has different terms. It can be called the bends, the chokes, the staggers, because if it gets trapped in your lungs, you're in a choke, you won't be able to breathe. You bend. If it's called the bends, it's because if it's in your stomach, you may bend over in pain, or if it's in your joints, you may bend over in pain. Hence the word. Or it could be the staggers, because if the bubble gets trapped in your brain, in those arteries or veins, that means that it can affect the surrounding brain tissue and can affect your mobility, your sensory stuff, or maybe even your ability to speak, or you may be in a coma. Like I said, you ascend too quickly. If you ascend too slowly, I'm sorry, you have to make sure that when you're doing that, because you are dealing with nitrogen gas, if you ascend slowly, you'll be fine. Avogadro's law is related to Avogadro, that guy, right? So dealing with moles. So volume of a gas and moles of a gas vary directly. They follow the same direction. V1 over N1 equals V2 over N2, similar to Charles's law, but now we're just dealing with um, volume and moles. So as the number of moles increase, the volume increases. If the volume decreases, the number of moles decreases, as long as pressure and temperature remain constant. So a real life example is you blow up a basketball, you're forcing more gas molecules into it. More molecules, greater the volume, therefore the basketball inflates. As you take a deep breath in, your lungs expand, filling with air. Exhaling decreases the volume of the lungs as you're getting rid of those molecules. Combined gas law. PV P1 V1 over T1 equals P2 V2 over T2.